Many of you will know us in the financial space because that's where we've been very successful. But we do have success in a number of other spaces as well. In terms of a little bit more detail, we have our adapters, our software-defined NICs. Very useful for storage. I'm going to talk about a number of these things. NVMe OF or NVMe over Fabric. Financial trading, telco. I'll give you a focus on web deployments and particularly Nginx and database applications. We have our network analytics and forensics. This is where the title comes from, the wireless, the wire, which we'll see later. For packet capture, network analytics, visibility. Also in some spaces for compliance, regulation, and security. And then we've recently introduced a range of security products, which is the adapter actually doing firewalling and traffic logging capabilities within the NIC with SolarSecure, Domain Fortress, and Serverlog. So that's what I want to cover in the presentation. Hopefully I'm going to get all of this done in the 30 minutes or the 29 minutes that I've been allocated. So in terms of trends in the data center, yeah, we've heard a number of things today, OCP, containerization, etc. One thing that you see a lot is scale out. Scale out is the architecture of the web's applications used. If you want to have more capacity, you add another server, you add another application. It's already been talked about containerization. I've heard less today about NVMe. I'll be covering that. Telemetry is down at the bottom, which is our capture and security. So let's get started and go through them. So Solar Capture is our capture capability. Solar Secure is our security capability. The other one is a little bit less inventively named. On-load kernel bypass is the technology we have to accelerate the rest. Some trends, and yeah, please feel free to comment and ask questions as we go through. On the top line, a while back, you would have a server with 1 or 2 processors, 1 core per processor, 1 thread per core, 2 threads per server, a rack of 38 servers. Appreciate that you can go to slightly more, particularly with the denser solutions, but not in those days, giving you something like 76 threads in a rack. That effectively meant the rack could do about 76 things simultaneously. Along the bottom line, 2 processors per server, 32 cores per processor, 2 threads per core, and the numbers are going up, 128 threads per server, nearly 5,000 threads per rack. Bottom line's easy, that's 2017. Anyone want to take a guess of how little time ago we were looking at the top row?
2012.
No, don't be further back than that. I think it was 2001. I think 2001 is when Intel started with hyper-threading and doubled the core count per processor. Before that, 1 chip was 1 CPU, 1 thread, you got 1 application running at a time. Yes, you had multitasking, but there's only actually 1 running at a time, and then it switched to the next one. So things have changed. What that's meant is, over time, the point is that we've now gone from 76 to nearly 5,000. That's a significant increase in the number of things that are running, and therefore the number of things that need to connect to each other. Fortunately, in our adapters, we have the ability to have 2,000 queues, which means that all of these things can talk to each other quite easily. The other thing that's changed recently is the traffic, and this is a study that Cisco did, showing growth in east-west traffic. A few years ago, I was thinking, well, we're going to be a bit stuck with this 10 gig stuff. What are we going to use it for? Talking to the data centers and the ISPs, and they've got 140 gig coming into this big data center. Well, 140 gig was 14 connections. How are we going to sell more than 14 ports? But what's actually happened is the ingress to and from the internet is the small bit at the bottom according to Cisco's study. A lot of the traffic goes between the servers within the data center, and it's even higher if you count the stuff that stays within the rack. So within that rack of 5,000 possible threads, you can have a significant amount of traffic that never leaves the rack. As that has grown, and so you've got the statistics from the Cisco white paper, as that's grown, protecting servers from each other has become more important. Your firewall is hopefully protecting you from the outside. What's protecting you from something that's got inside already, particularly if you're hosting other people's services? What stops that attacking another customer of yours? So we're talking about that. So, zooming in, the software-defined everything scale out and the NVMe flash storage, the ones I talked about first. So, our adapters, they go all the way down to the bottom. They were exactly the same at the bottom end as anyone else's general purpose adapter. We have adapters at 10 gig, 40 gig, that's sort of a speed range. So they are cost effective down at the bottom end. However, what we do within that adapter is we do a number of things that you would get in more expensive solutions up here. So we have packet processing at binary. That's sort of a given these days. But we have very flexible capability. We have the ability to do filtering rules for when we're doing security. We have ultra-low latency, which is where we've really made our name in the trading networks. We can do transactions sub-microsecond. So very, very fast. We are programmable, and say we're inexpensive, we're at the same price as these general purpose NECs, offering an amount of the capability up in this space. In terms of the software, and I appreciate this a busy slide, but I just wanted to show how things fitted together, ready for the next slide. We have, within the server, the kernel space and the user space. This is key to us, this user space. User space is where applications run. We run a lot of our logic in user space, which avoids using the kernel. If you avoid using the kernel, you save a lot of time doing context switches that the processors have to switch. That can destroy cache, a number of other things that make it efficient. So you'll notice that a lot of our stuff actually sits here in the kernel space. In order to do that, that requires capability down here in the adapter, because the kernel is normally doing your security. It's keeping one application separate from another. It's providing the filtering and the steering of traffic. Because we do that, and we want to take advantage here of user space, we push those functions down into the card, and you have to have the hardware logic to do that. So, what that delivers is the ability in an Nginx environment to deliver typically around 30% more requests per second. If you go out to a table in the other room, you'll find a white paper that explains the testing methodology we did to achieve that. And the paper actually says we get 108 to 128% improvement. That's the optimized test. That's not the one that you're going to be running every day. That's just making a new request. The 30% is the more realistic number that you're likely to achieve in real use cases. And what that means is that you have to allocate less cores to do the same amount of work. You've heard about containers today, and containers and virtualization. This one sort of visually indicates the context switches. So when you keep all of these separate and go via the kernel, every time you do that to send and receive a packet, the kernel takes out of your CPU time. We get a lot of that back by allowing user space to talk directly to the card. It gives us the ability, particularly in the virtualization space with VMware, we can run 40 gig per guest, if that's the performance the customer needs. We don't tie up the resource in the hypervisor, or in this case in the kernel. NVMe storage in Flash. Project going fast, I've only got 30 minutes and I've probably got that much left. We hear a lot about NVMe now. The different places that you can put it. You can put it in the server. That's quite common. A number of the server vendors now have the ability to put in 4, even up to 24 drives into a server. You can put it in another chassis and just have some more if you run out of capacity. Or you could try and do this across a fabric. What is that fabric? Essentially that fabric is an extension of the PCMA bus. You can cable it with PCMA extension cables. It's more normal to cable it with some sort of fabric. How do you do that? There are a number of choices. RDMA is one that often comes to mind that people talk about. In order to run RDMA, you need a network that supports it. If you want to run RDMA over Ethernet or Rocky, you really need data center bridging in your switches. So of all of those 100% of the switches out there, and this was an IT brand pulse survey, they concluded that 99% of them, so nearly all of them, are running IP. However, only 25% of them support data center bridging. Data center bridging is really a requirement to run RDMA. That's not 25% of them are configured to run it, 25% of the products support it. And you get down to 0.2% that are actually installed and running the protocol that you would need to run your RDMA over your Ethernet network. So, when you look at how do I connect all my NVMe together, this is what you end up with, a choice. You either use fibre channel, this one here over data center bridging, this one here using iWalk, and this is the one that we more recently contributed to the standard, which is to run over TCP. That TCP will then run over 99% of the network rather than 0.2% of the network. And it makes it a lot easier to provide that connectivity. What does it do in terms of performance? This was the performance we got when we first tested it, using our cards obviously. And we are within 10, 20 nanoseconds of the performance. It's a dangerous statement to make because if we ever get better, we'll be claiming it makes a big difference. But 10 or 20 nanoseconds on these transactions is quite a negligible amount. Effectively, we were about the same. That has been improved, and we've cut those differences in half now. However, what it does give you is the flexibility to run NVMe over IP. What that means you can do is if you've got your rack with some rack space that's free, if you choose to, you don't have to keep consolidating your rack. You can just fill in, plug some NVMe in here, some NVMe in here, and connect them together with Ethernet. Why do we call the presentation why the wire doesn't lag? So this is the key one. Not all of you, some of you from vendors, so maybe you haven't been in this position, but if you talk to a customer, they will probably say they're one of these two guys. So the guy says, had a bit of a problem on the network at lunchtime. His boss said, well, what was it? He doesn't know. He doesn't actually know what happened. So if you're nodding that you've been at least one of these two. He wants to know if it's going to happen again. The problem is you don't know, so it's a maybe. You don't really say that to your boss. Your boss gets a little bit angry and says, what are you going to do to prevent it? Well, the problem is, you didn't know what it was that caused it, so how are you going to prevent it next time? He doesn't really want it to happen again, and you're going to have to, don't worry, you're going to connect an analyzer, and when it happens again, and that's like a red flag to the bull, he doesn't want it to happen again because when it happens again, there's financial cost, there's hassle, etc. So how do you prevent this?
You kill the boss.
Sorry?
You kill your boss.
You could do that, but he may be the one to sign your paycheck, so that may not be a good idea. The problem is that analytics costs money. Effectively, you're asking someone to monitor what you're doing, and it's going to potentially do all the work of the web server you're monitoring, for instance. So you can spend a lot of money on hardware, software licenses, and processing power, and therefore power, etc., to do the analytics, just to check that the thing that's doing the right thing is doing the right thing. A solution must be able to handle high data rates and high packet rates. It's not much good if it misses something. And this is a contrived example. Buy 1 million Microsoft shares for $101.01. Now the protocols deal with some of this, but it's a good example. The receiver receives buy 1,000 Microsoft shares for $101.01. And you can see his network engineer is sweating already. Someone wants to know what happened to the missing packet. Did the sender not send it, or did the receiver not receive it? And if you're responsible for the network, you want to know whether you can blame the sender for not sending it, or whether you have to admit you lost the packet for them. So you go and check the capture logs and see what it captured. And the capture says, buy 1,000 Microsoft shares. Great, the sender didn't send it. I can point the finger. However, you'll notice on the right, it also missed here and it said buy them for $10. Clearly the message is wrong. What it implies the capture is wrong. If the capture is wrong, how do I know the sender didn't send it? It could be that I didn't manage to capture it either. So it makes debugging hard, probably impossible. So how do we address that? So we have a range of capture boxes that will do line rate. Here are some of the screenshots. The solution we provide is hardware only, hardware and the software that goes with it. You can build your own appliance or a complete appliance that is ready to plug in and go. It comes with a database, a GUI, and all the things you need to present it. The thing that we generally do that is different is we capture everything lossless, so you've got everything. You don't have to go and analyze it all the time in real time. If an event happens, you then go back and analyze what it was that happened. So when the guy had the problem at lunchtime, he goes back, like you rewind your TV, looks at what happens, analyzes it and says, there's my problem. So here's the access to that data. It's like the OCP platform. It's open. You can get to each of these blocks. You can run your own analytics if you want to in real time. And we have many customers that add to this in terms of capabilities. You'll notice here a number of open source third parties that we work with: Snort, Sericada Grow. They're all rules-based security and analytic engines. Wireshark, you probably will know as Packet Decode. Packets of this is in the financial space. Hadoop is a clustering capability for big data processing. Splunk is a text-based indexing. And then there's Kibana and Elasticsearch, etc. A range of packets, products, how long
You have 8 minutes left.
So it starts at the low end for 4x1, 2x10, going all the way up to the larger end, 2x40. It can sustain a 740 gig port before compression. It does slightly better with compression. With 200 plus terabytes, if you're compressing that data, it could be half a petabyte. And that's before you start expanding. So we have a real range of capacity. Or you could build your own one at the bottom using the software and hardware configuration. The hope is that if you're this guy, you can say to your boss, we had a problem on the internet at lunchtime. It was at this time. We also have time synchronization software called PTP. PTP is a standard. We support it in our card in the hardware, which allows you to synchronize hosts within about 50 to 200 nanoseconds. You can very accurately pinpoint the time at which something happened. You might not want to go and tell your boss that it happened to the nearest nanosecond, but what it allows you to do is if some event happens here in the network at a certain time, when you go and look somewhere else, you're not looking for the whole second's worth of data, maybe you're looking at half a millisecond. You're narrowing down what you have to look at. So he looked at the capture, said it was a BGP problem, he's fixed it, he's put procedures in place to make sure it doesn't happen again. His boss is also very happy and of course rewards it. That doesn't always happen, but it's nice to think it does, isn't it? In terms of what we offer there, lossless, up to 40 gigabit, timestamping, increased visibility, minimum time to detect, repair, diagnose, whatever you want, is the tools that allow you to find out what happened. Why? It also allows the security guys, the forensics, to go back and, okay, we had a firewall breach. What exactly happened at that point? How much data did we lose? How many of these reports where someone says, we lost 5 million credit card numbers? Did they lose 5 million? Or did they have 5 million and they got breached, therefore they don't know how many they lost? If they had a log of what left, then maybe they would be able to say, we had a breach and we lost 73 credit card numbers. At worst it's not going to be as, the worst it can be is as high as the number they had. Maybe they didn't get hacked quite as badly as they thought, and they can go and diagnose it. If they can diagnose it quicker and fix it quicker, obviously that's good for everyone. And then the product range. So focusing on the security, this is the product that we announced at the Black Hat Summit back in June, July, I think it was, in Las Vegas. What we have is obviously with the traffic east-west growing, then there is a bigger demand to be able to protect yourself. However, putting a firewall on every server, if you're going to do that in hardware, people aren't going to buy 1,000 servers at 1,000 port firewall. They don't exist. On the other hand, they're not going to buy 1,000 firewalls with 2 ports in and connecting in front of every switch. You don't have the rack space to do that. So your options are, traditionally, software-based firewalls, which you put into the server. The problem with software-based firewalls is all of that valuable processing time is now being used up, not all of it, but a percentage of it is being used up processing the firewall rules. The other big issue is that some developers and some applications do require root access. So they have access to the box. If they've got access to the box, they can go and turn it off. If you get hacked and someone gets root access to your box, they can turn off the firewall rules. If they turn it off and you don't notice, you're left open. So what we've done is we've actually taken the firewall rules and put them into the adapter. We put them in the hardware. We have an encrypted link to the hardware to talk to it, which means a separate effective password. We use certificates and encryption, of course, to set the firewalls in the adapter. What that means is that even if you have the server compromised, the rules will still exist here. Obviously, we don't have our adapter in every host yet. We would quite like that. But the adapter, the network adapter, is something that will exist in the host, whether it's ours or someone else's. So it's non-additional hardware to provide the capability here, separate from the server. And we can process those rules in about 50 nanoseconds. So we're not even adding a significant overhead. The reason we can do that is when I showed at the beginning, the fact that we took some of the responsibility away from the kernel. One of those things that we took away from the kernel was the ability to decide where traffic goes. We effectively have to do that lookup on every packet, so we reuse that capability to say we know where these packets go, and some of them go in the bin. We don't allow them to get through because they're blocked. That allows us, even if you don't use it in force mode, to use visualization techniques to show who talks to who. You set policy. Even if you don't implement this as security, you can say, well, these ones met the rules. These transactions here are new or unknown. I should investigate them. And maybe you then should set a rule that says I block them. People will take the view that I'll block everything and then start to let things through. Others will take the view that my network works today, I'm not going to suddenly turn everything off and this is what happens. So you can basically work through these to turn all of these red transactions green. To say, okay, yeah, I've accepted that one, I've accepted this one, until my network is green. At which point, anything that pops up as red is something to be investigated. Pops up with a time frame on it, you go back to the capture and see what it was. So in summary, we have the bandwidth, we have 10 gig, 40 gig adapters. End of the year we'll be starting to ship our 25, 50, 100 gig adapters. Very low latency for where latency matters. It doesn't matter everywhere, but for where it does, we are well under 1 microsecond for transactions. We have 2048 separate paths through the card, which means that we can queue the traffic to each of the cores and maintain connections between lots of different places simultaneously. For the Nginx, I talked about 30%. Excuse me. I talked about 30% increase in performance. For containers, there is an increase in performance, but the other thing that we allow you to do is to run significantly more. We can perhaps get 10 times as many containers running on the same box. The hardware security I've just talked about, and the packet capture is our instrumentation. If anyone has any questions, please ask, but if not, thank you very much for listening.
I have a question. So this packet capture, is this a software that runs on Unix, or is it an appliance, a box, or? The software runs on the host and uses the capabilities of the NIC. Okay.
That is packaged as an adapter plus the software to run on the host,
Okay.
or as a physical appliance. When we package it as a physical appliance, different people want different sizes, so someone may want a small box with 10 terabytes, someone else may want 200 terabytes, therefore there is more than one model. When we package it as software with the card, the customer is providing the server for it to run on, therefore they can choose how much hardware they put, so there's then one configuration.
Okay, thanks.
So you suppose they are installed everywhere?
Sorry?
You suppose they are installed everywhere?
Which? Capture or?
Yeah, capture.
Yeah, so the capture, because we are doing the capture and we do it on our card, which is a high volume card. We sell tens of thousands of these cards every month. That allows us to be reasonably priced in the capture space. How much the customer decides to deploy that is up to them, but the cost per capture unit is significantly less than some of our competitors. So you can deploy it in more places. Obviously, the more places you deploy it, the more chance you've got of spotting a problem if it occurs. If we were a quarter of the cost, you could spend half the money on deploying twice as many places. You could spend the same amount on deploying 4 times as many places.
Because there's a related question that you need to record every data, right? And then you need a powerful storage system.
Yes.
Then where do you place this storage?
So, most people think, well, why don't we just transfer this across the network and use NVMe? You can do that. Generally speaking, it is transient storage. You want to store it for 24 hours, 48 hours. Some of the customers with real transactions want to store it longer. So the best place to do it is not to have to keep moving it around, generating more traffic, and store it locally. So most of the configurations will put in 10 to 200 terabytes in the same box that does the capture. Now you may pick key points in your network to do that. That may be in a financial thing, the egress to the exchange, where you're going to do the trades in a web environment with connections to web servers. It may be on the internet connection to the for the web traffic. You obviously have to balance how many you put in, what capacity you go with. If you don't provide enough capacity, you just overwrite the data quicker. You'll have to notice that something went wrong.